Hi Rockridge, this is Mrs. Berger, and today we're going to talk about adding, subtracting, and multiplying radicals, building on our skills from Unit 2, Day 1, where we simplified radicals. So the first thing we talk about in adding and subtracting radical expressions is the fact that we need to do something of a combining of like terms, okay? You cannot add or subtract things that are not alike. The index has to match, or the little number above the shelf here, and the radicand, or the thing underneath the radical, has to match. Otherwise, we can't combine those like terms. So if we look at this first example here, negative 5 square roots of 3 minus 3 square roots of 3, we do in fact have square roots for both of these, and we have the square root of 3 for both of these. So I would call these something of a like term situation, and so we have negative 5 of them and negative 3 of them to make it a total of negative 8 square roots of 3. So it's kind of like having a variable to combine, okay? But they have to have the same radicand and they have to have the same index. On number 2, once again, we have the same index. They're both square roots, not cube roots or fourth roots or anything like that. They're square roots, and they're both the square root of 8, so they match underneath there as well. So we have 2 of them minus 1 of them leaves 1 positive square root of 8. Now the second step is we should always check to make sure our final answer can't further be simplified, the thing we learned last lesson. So let's check and make sure there's nothing to be simplified here. We're taking square roots, and I believe there is a square root of 4 in here, right? We can break this into the square root of 4 times the square root of 2. So we need to think of this as 2 times the square root of 2. If you did a factor tree to pull out 3 3s and then circled 2 of them, that's fine too. But we should not leave our final answer as the square root of 8 if it can further be simplified. That didn't happen on number 1. We can't further simplify the square root of 3, but it did happen here. So make sure that you always check for simplification options. Alright, number 3, we have square roots again, and we have the square root of 27. The same radicand is found underneath here. So we're allowed to combine those. Negative 3 of them, minus 3 of them, minus 3 of them. So we have a total of negative 9 square roots of 27. We need to check for simplification though. If we look at that 27, there actually is a perfect square in there, right? 9 times 3, and that 9 gets broken further, so that we can pull out this right here. So then we have negative 9 times 3, since we need to take 1 3 out of here to represent this pair here. We take 1 out to represent it, and we leave behind the square root of 3. Our final answer is negative 27 square roots of 3. Some of you may wonder, what if I pulled 9s out of the square root of 9s out of all of these first? That's totally fine. If you did that, you will end up with the same thing. If you wanted to simplify each individual thing first, that's totally fine. I just saw that they were all matching, so I took them out all at the same time. Alright, now number 4. We come upon number 4, and we do have everybody matching in the type of index we have. We all have square roots here. However, the radicands, or the things underneath the radical, don't match. However, when we look further, we do see that we could possibly simplify a couple of these. Not the square root of 3, that's pretty much stuck the way it is. But we could further simplify these. And when we simplify these, we may find matching friends. So let's do that. Let's break 12 into 4 and 3, and then break 4 further down. So we found a nice little pair here. We're going to pull that pair out, and we're going to leave the square root of 3 behind. Then let's go ahead and look at, we know we can't do anything to the square root of 3, but we can do something to the square root of 20, right? We can break that into 4 and 5, and then further break 4 into 2 and 2. So we found this nice little pair here. We are going to pull out one of those 2's to represent that pair and leave behind the 5. And then I'll go ahead and pull down 3 square roots of 3 and see what we have left here. we have negative 6 square roots of 3 plus 3 square roots of 3 plus 6 square roots of 5. Since we have square roots of 3 here, those can be combined. So we can have negative 3 square roots of 3. But this square root of 5 is not the same as the others, so he doesn't have any friends to combine with, so we'll just bring him down as is. There's nothing more to simplify there or combine. So we have negative 3 square roots of 3 plus 6 square roots of 5 is the simplified version of this problem number 4. Alright, another example, number 5, gets a little more complicated. We've got 6th roots and 4th roots and 6th roots and 6th roots. So certainly this 4th root can't be combined with anybody. We will check for simplification, but it can't be combined with anybody else. We have a 6th root of 3 here, but these are 6th roots of 192. So we're going to have to do a little bit of combining, a little bit of simplifying, and we'll see as we'll keep going until there's no more simplification or combination to be done. Okay? Alright, this 4 times 6 of the 6th root of 3, there's no more simplification, so he's going to come down as is. But when I look at this square root of 32, 4th root of 32, that actually has a 16 times 2, and 16 has a 4 times 4. And each of these 4s can be broken out, so that if I have an index of 4, I'm looking for groups of 4, and I found them right here. Okay, so that means I'm going to take, I already had a plus 2 out front, I'm going to take one of these to represent that grouping outside of the radical, and then left behind is this guy right here, this leftover 2. So that's going to be 4 times the 4th root of 2 left over there. Now, I am going to make things a little bit simpler on myself. I'm going to say there are negative 3 of this thing and negative 2 of this thing. So I have negative 5 6th roots of 192. Now, I start breaking 192 into its components. I remember my 6th roots, and I remember that there was a 6th root that had a 2 to the 6th power somewhere in here. So I thought to myself, isn't 192 divisible by 3? It is. 192 is 3 times 64. 64 is 8 times 8. Each of these can be broken into 4 times 2. And each of these can be broken into 2 times 2. So I've got to bring all of these factors down. And you need to come down here too. So that I have 1, 2, 3, 4, 5, 6. So I have 6 2's. And I needed to find a 6th root. So if I have negative 5 out front already, I'm going to take one of these and represent this grouping of 2 outside. And then I'm going to leave behind this 3 that didn't have any friends. It didn't have a group of 6 3's, so I had to leave behind the 6th root of 3. So this will be negative 10 times the 6th root of 3. So that's what all this comes down to. So I have 4 times the 4th root of 2, negative 10 times the 6th root of 3, and then this couldn't be combined with anything, so it comes down here as itself 4 times the 6th root of 3. Now, the blue things have the exact same index and the exact same radicand, so those can be combined. But the 4th root of 2 doesn't have any friends. It doesn't have any other things that have this same index and this same radicand, so that's going to stay the same. So 4 of these things minus 10 of these things is negative 6 6th roots of 3, and then we just bring this straight down, plus 4 times the 4th root of 2. So that is your simplified version of this problem. Okay? So pause the video and go back and check that if you need to see any of that work done again. I definitely used factor trees here to show them visually. If you don't need that, if you can break these into the parts and pull things outside of the radical without factor trees, you're more than welcome to. Now I want you to try the practice, the next 3 problems on the practice. I want you to pause the video and then come back and check your answers. Okay, so pause the video, try these on your own, and then come back and check your answers. Okay. take a minute to check your answers here. If you need to pause and stare at the work for a little while, please do so. But hopefully you got these three answers after you looked at these. Remember, the cube root of -1 is -1, so that's why that pulled out here. And you do need to remember things like the cube root of 27. You need to be looking for those things that we saw in that chart on day 1. Alright, let's take a look at multiplying now. So multiplying radical expressions, the key to this is you need to multiply the outside times the outside and the inside times the inside. So things on the outside get multiplied, things on the inside of the radical get multiplied. The indexes have to match, right? So these have to be both the cube root in order for this to work. And then of course our last step is always going to be check for simplification. So let's see how that works on number 1. There's nothing on the outside of this radical, so there's no outside times outside step to be done. But there is an inside times inside. So let's go ahead and do that. So this is the cube root of -60. Now, we know that there's something more in here that we could pull out, right? Definitely the cube root of -1. We definitely know that we've got the cube root of -1. And is there any other cube root that we can think of that's sitting in positive 60? We can think of 6 times 10, 6 can be broken into 2 times 3, 10 can be broken into 2 times 5, but that's just 2 times 3 times 2 times 5. There are no groups of 3 within 60. So we actually only have cube root of 60 as a radicand under there. We have to stay with that. We can take the cube root of -1, so we'll go ahead and say that the answer to this is -1 times the cube root of 60. And if you want to write this just as negative cube root of 60, that's fine as well. Okay. Number 2. Again, we have nothing on the outside here, so we'll only multiply the insides. And we do have the same index here. They're both square roots. So we can make this the square root of 15. Again, we'll look inside to see if there's any perfect squares in here. There's only 3 and 5. And both of those are prime. You can't break those into any further perfect squares. So this is the final multiplication of those two radicals. Number 3, again, we have nothing on the outside, so there's nothing to be multiplied there. But when we multiply the insides, we have 6 times 2, which is 12. Now, unlike up here with the square root of 15, there are perfect squares sitting inside 12. There's a 4 times 3. And we know that 4 can be broken into its perfect square. So we look at here and find a nice pretty pair. So we're going to take one of that to represent that pair outside, and then this 3 is left behind under the radical. So that is the simplified form of that multiplication problem. Now on number 4, we actually do have things on the outside, and we're distributing. Just like any other distribution problem, we're going to distribute this into the 4 and this into the -3 square roots of 5. So let's see how that works. First, we have outside times outside. The 4 is not under a radical, so he gets paired up with the 3. So that's going to be a 12 square roots of 3. And then 3 times -3, those are both on the outside of the radical, so they get multiplied together. And then square root of 3 times square root of 5 turns into a square root of 15. Now we look inside to see if there's anything to be broken out. There's no perfect squares here. There's no perfect squares here. So we're actually finished with this problem. There's nothing else to be done or simplified or combined. So 12 square root of 3 minus 9 square root of 15 is the answer to that multiplication problem. Let's distribute again. Remember, outside times outside, that's -12. Inside times inside, that's square root of 60. Plus 20, 5 times 4 is 20, times the square root of 15. Now, oops, this was 90, sorry about that. Fix that real quick. 15 times 6 is 90, sorry. Alright, now we need to look and see if there's any further simplification we can do. Within 90, there are perfect squares. We know there's at least one, right? There's a 9 in there. Within 15, we know there aren't any perfect squares. There's just a 3 and a 5. There's nothing else you can do. So let's take care of this. There's a 9 times 10 and this can break into 3 times 3, and the 10 can only break into 2 times 5. So, and again, the index is 2, so we need groups of 2. There's only one of those, so there's just that. So negative 12 gets joined by the 3 that comes out to represent that grouping, and we leave behind the square root of 10, plus what we had up top, 20 square roots of 15. Now, the indexes match, but the radicands do not, so these cannot be combined. So we actually have the final answer of negative 36 square roots of 10 plus 20 square roots of 15. Now number 6 is actually a very similar problem to anything that we would have done in Algebra 1, a FOIL problem, first times first, outer times outer, inner times inner, last times last. And we'll take this one step at a time. So first times first, those are both outside the radical, so that's negative 28. Outer times outer, the negative 7 is on the outer, the square root of 3x is inner, and there's nothing to be combined there. Inner times inner, the 4 stays outside, the square root of 3x stays on the inside. And then last times last ends up being square root of 9x squared. So now we combine what we can. The negative 28 doesn't have any friends. Square root of 3x and square root of 3x match. Both the index and the radicand are exactly the same. So we have negative 7 of them and 4 of them. So we have a total of negative 3 square roots of 3x. And then since 9 and x squared are perfect squares, we will pull both of those out as 3x. There's nothing similar here. 3x and square root of 3x are not the same, so they cannot be combined. So this is our final. And we should actually put an absolute value around that x to be proper. Alright, another FOIL problem. First times first, outer times outer, inner times inner, and last times last. Now let's see what we can combine. Let's see, we have negative 4, that doesn't really have any friends, plus 2 times square root of 5k minus 2 times square root of 5. Those are not alike. I cannot combine those. I could simplify this a little bit to make this 5 times the square root of k by taking that perfect square of 25 out. But that's really all that I can do to combine this. So the most simplified version of this is this big long thing. Negative 4 plus 2 square roots of 5k minus 2 square roots of 5 plus 5 square roots of k. So that's all that can be done there. Alright, let's put our multiplication skills to work on these 3 example problems. You go ahead and try them. Pause the video before revealing the answers. Pause the video and try these out on your own, and then check your answers by pushing play. Alright, hopefully you got the same answers I did. 3 for the first one, 10 times square root of 6 minus 12 times square root of 10 for the second one. And this nasty one is the last one, 3 minus 4 square roots of 15x minus 25x, and we should have absolute value around the x. Because remember, our special rule, if we take the square root of x squared, we should absolute value the x. Alright, you should have the skills to go ahead and go into your homework number 2. Remember to simplify everything at the end if you have any other simplification steps, and ask your teacher if you have any questions.